This is ECE 207, isn't it? I've been in different states today, not geographic states, but as a reminder, homework number 8 will be forthcoming. It's not yet been posted, but it is already due. So you're going to need to finish that up in a week. Hopefully that won't be too difficult. A week from today a week from Thursday, there's some event on campus that may preclude us from meeting physically here. May be difficult, or maybe you wouldn't understand the lecture if you came. There's, I believe, a game going on that day, meaning I'm not going to have class. I don't think they're encouraging as many people to come to class or to come on campus. I'll try to record some material and make that available for you. That's the idea, or that's the plan. And that's for the 2nd of December. So you won't come to this lecture hall on the 2nd of December. Which means we really only have 3 more lecture times that we will physically be here. Today is one of those, a week from today, and then a week thereafter, and the semester is finished. Our final is on the 16th, I believe, which is a Thursday, and that will be, I think it's the 2 to 4 o'clock time slot for the final. What I want to do today is begin chapter 10. That's what homework 8 will be on, possibly homework 9 also. We'll talk about the physics of diodes a little bit to get you thinking about why these might work the way they do. We'll talk about the current voltage relationship of diodes, and then we'll look at how we can actually analyze a diode in a circuit, different techniques or approaches to doing that. A diode is like some of the other elements that we've looked at. It's a 2-terminal device. It's a little different than an op-amp, which had all sorts of different connections or pins to it. This just has 2 pins. Physically, or to think about this in terms of how it might work, is really it only allows current to flow in one direction for this particular type of diode. And the direction of current flow is labeled I sub D, and that corresponds to a particular voltage drop across that diode indicated from the anode end to the cathode end. And those anode and cathode, I'm not sure that I always remember which is which, but A comes before C, and the positive is the one that comes before to allow current to flow. I'm not sure how best to remember that because I'm not necessarily the best one to tell you how to memorize something. But this is a 2-terminal device. And it's a particular kind, or made out of a particular kind of material. It's a semiconductor device. This particular component actually has a nonlinear current voltage behavior. In particular, if this is our axis, here is, let's say, the voltage across the diode as I had just sketched. Here is the current through that diode. The forward current voltage behavior looks somewhat like that. Once it gets turned, or it turns on, current starts flowing at a certain voltage, it almost just stays at that particular voltage, V sub D, which typically, depending on the type of device, a lot of ours will just assume that's 0.6 or 0.7 volts is V sub D. It's not very big. And this might actually be, in terms of units or scale, sort of milliamps that you want flowing through your diode. Question? So the current is not going to go to infinity. The question was, does the current go to infinity? Ideally, yes, it will support an unlimited amount of current, but for an ideal or for a practical diode, you can only put so much current through it before it starts being destroyed. You smell it, or smoke starts being emitted from the device. You can actually reverse bias the diode, and really very little current flows, meaning now we're talking in the nanoamps, so a factor of 10 to the minus 6 less in magnitude, until you reach a certain point, and then it actually breaks down, and then current really starts to flow again. And this is now the picture that you could sort of think of exists between, or the relationship between voltage and current across this two-parameter device, which is a diode. Physically, what this could represent is a one-way valve, where maybe we have a stop there, and there's sort of our gate, which, depending on this fluid that's flowing, the fluid will only go in one direction. If the fluid was actually going from right to left, it would bang up against that stop and not be allowed to flow from right to left. We will have fluid going from left to right, which in our diode model or schematic, the current is going to go in the direction that the triangle is pointed. And this, schematically, this diode is much smaller than an op-amp's triangle, and the op-amp triangle does not have that vertical line at the output terminal or pin of the op-amp. So maybe to you this looks like an op-amp picture, but this doesn't have two inputs, it just has the one input, or it's a two-terminal device, and current can flow, but it only flows in one direction. The reason we might want such a system is because it opens up more possibilities for applications. Just like a one-way valve might be important in a fluid problem, if you plugged in a voltmeter to this outlet, you would see an AC waveform. But to power some device, which you might have in your ears right now, or to charge your music, you may need DC, direct current, more like a battery. These can be used to make that conversion possible. Diodes can. So that's one application would be an AC to DC converter. We can also use these in different configurations to modify or shape different waves. Meaning if we had a sinusoidal wave, maybe we only want to preserve the top half or the positive portion of that sinusoid and cut off the negative portion. That would be a wave shaping circuit. We also can use these if you had something that you wanted to make sure that you were only applying 5 volts to this device, and you actually had a source that was fluctuating in terms of its voltage level between maybe 6 volts and 12 volts, but you wanted only 5 volts out, you might want to build what's called a regulator. And diodes can be used in regulators. Diodes can also be used to help prevent some big currents that can exist, or it gives a path for current to flow when you stop the current from flowing in, maybe I shouldn't say an inductor, but in inductive loads. And that's somewhat analogous to in your washing machine, when water's pouring into the washing machine and all of a sudden the valve closes, and what happens to the pipes? Do you ever hear a sort of a shaking? Maybe you don't hear that, but you hear something that says it's not happy. Well, that's what happens when you stop current flowing in an inductor. What's our relationship for current and voltage on an inductor? Eli. V is equal to L di dt. So when we stop the current, we have a big di dt, we have a big voltage spike. And that's not a good thing to have. And so we would like to maybe allow that current to be shunted around that inductor. Or motors, when we have motors, they look very inductive, as we learned in the power material. And if you're now turning that motor off and on, you may have this inductive load being turned on and off, and that may not be a very good thing for some of your circuitry, and you may want to shunt that, or may allow that current to flow around that particular device when it's turned off. Let's talk a little bit about the physics behind these diodes, now that we've explained maybe a little bit about the application for those. Now I'm going to just get us thinking about what we have maybe thought of up to this point in the lecture. We've talked about conductors, which are the wires that carry our information or our signals, and that might be made out of silver or copper. We might want to try to keep that current from flowing in certain situations, and so we might actually want some kind of insulator, which might be rubber or glass or Teflon. And this particular axis that we're sort of going vertically on is our conductivity. That tells us how conductive are these particular devices or elements. We have things that are really conductive, which are our metals, silver and copper, and we have things that aren't so conductive in rubber, glass, and Teflon. Well, we've discovered that it's nice to be able to work in between those two extremes, and that's where these semiconductors come into play. And you've probably heard of these elements, germanium and silicon. Our devices are now that we're making these diodes from are semiconductor devices, and the base material might be silicon that we're building these with. And that allows us to have these devices operate in several states or conditions. Sometimes maybe they'll look more like an insulator, sometimes they'll look more like a conductor. But being in between, they have that possibility or that potential. The way that we can create these, well, if you look at these pieces that we've just uncovered on a periodic table, let's look at the outer band of electrons in these elements. We have our 3, 4, 5 elements in the periodic table, where this one has 3 electrons in its outer shell. The 4 is plus 4 in terms of electrons, and 5 is plus 5. Some possible elements that we might use then in these particular columns: we have boron, which is B, or of atomic weight 5. We have carbon, 6, and we have nitrogen, 7. Then if we go a row below that, we have aluminum, we have silicon, and we have phosphorus. And the ones that we are going to play more with or talk about are, let's say, a 3 valence of boron. We have our silicon, which might be our base element, and we have phosphorus, which is our 5 element, and we may now play with combining those into certain devices. That's the idea. And what we're wanting to do now is get doped up. I'm sorry, we want to dope the silicon. I thought you guys were asleep. You just didn't look like you were quite there, so I wanted to wake you up a little bit. We now have silicon. That's our base. That starts with 4. Now what we want to do is dope that with either a 5 element or a 3 element to give it more intrinsic behavior, or make it act more like a 3 or a 5 device in general. And that's what's called doping. Or now we have doped silicon. And the reason that we want to do that is silicon looks pretty benign by itself. It has 4 electrons in its outer shell. If you start building that together, it's going to have 4 and 4 and 4. They're all going to start sharing these electrons, and their outer shell is going to look full to its neighbor or to each other. What we want to do is introduce some 3s or 5s to try to either have sort of lacking an electron or having an extra electron in that outer shell, effectively, when you have them put together or built up. This allows us better conduction in our silicon device. These particular elements that we're doping with become donors, or what we call donor. And we could say now that we are going to introduce some impurities into the silicon, and we're going to call those then donor impurities. If we have a type 5, or type 5 elements, then in our outer shell, it might like to just have 8 elements in it. The silicon has 4. The phosphorus now is 5. Now we sort of have 4 plus 5, 9 elements floating around in this outer shell that only really wants 8 to have this nominal behavior. And because of that, these type 5 elements are effectively donating extra electrons to this lattice that's made out of silicon. And because it now has free electrons, we think of those electrons as having a negative charge, which we then call this particular material, that's silicon doped with a type 5 element, we call that an N-type material. Pictorially, if you view this, let's say here's a phosphorus element. It now has 5 electrons in its outer shell, which I didn't really draw 5 at once. I'm now having it share its outer shell with silicon. And hopefully you get the idea of what I'm trying to do. If you just keep building this up, this particular silicon might donate that guy, this one might donate that one, this one's that one, and that one's that one. But now how many does the phosphorus have so far in my picture? If it claims all of the ones that have not been circled, how many elements in my outer band or shell in my phosphorus do I have so far depicted in that diagram? If they're not circled, I have 8 around that P, but P should be having how many in its outer shell? Should have 5. So right now, if you count the ones that are not circled in blue, how many do I have? 4 just around the P. So this guy really has, there's an extra electron that is around that phosphorus element inside this picture of, or this diagram. So here is effectively our extra electron. That's what calls this, when it's doped with P elements, now we have more N-type material, or this is now an N-type material. Now the other thing that you can note, but this will, I mean, we haven't changed the chemistry of the phosphorus. It still has 5 protons in its nucleus, so it's still really a neutral element. But in the scheme of this, in terms of the outer electron shell, it's effectively like there's an extra electron out there. But this note is to just remind us there is also an extra proton in P to allow this system to actually be electrically neutral. That's what we have when we dope silicon with elements that are in the 5 group in the periodic table. If we did the same thing with silicon and type 3 elements, now what do we have? Well, instead of this being donor impurities, you could think of these as being acceptor impurities, meaning now we effectively have like free positive never fails, huh? Now we have free positive charge in the outer lattice. The the picture for that could then, or before I do that, let me just say, now instead of electrons, we have positive pieces, which we call holes, and we now have p-type material in this doped silicon, where we now have silicon surrounding the boron. This silicon is going to give us, or those four on the four quadrants will donate one, and then we have all of these others that share electrons in their outer shell. The boron contributes, it's a 3 element, it's only going to have 3 electrons that it's going to want to share with its neighbors, and because of that we now have this opening, or what's called a hole, appearing in this outer shell of electrons. So here is our missing electron, or what we might call the hole. And that's because this boron has 3 outer shell electrons. But the B, or the boron, only has 3 protons also, so it's electrically neutral. This whole system is still electrically neutral, but it has these nice properties where it's now missing an electron in the outer shell, or it now has an abundance of holes, whereas a phosphorus or a type 5 material has an abundance of electrons. What we want to do is, now that we're in this chemistry kitchen and we've created these 2 different elements, why don't we make a sandwich? What happens if we put 2 of these together? We put a P material and an N material together. What kind of behavior or characteristics are we going to have? Or what happens when this N and P type material are sandwiched together? And now that you're thinking food because of 2 days instead of meeting, you might be eating, you can start thinking, oh, sandwich, a P material and an N material. I can make a diode. So now you're starting to think about what you're going to be tested on during the final exam. This now gives us a diode, this combination or sandwich of 2 pieces. Schematically or pictorially, here's our diode. And we have it in 2 pieces. We have our what's that piece called? This is our P-type material, and we also have the leads connecting to those pieces of silicon or doped silicon. Here's our N material or N-type material. This was our anode. This was our cathode. On the left, or in the P-type, we have a high concentration of holes. And And on the right side, or the N-type, we have a high concentration of electrons. And if we were asked what's going to carry the charge on the left-hand side, we would say, well, we have extra P-type material or extra holes. The holes must be carrying the charge over here. And you might hear that referred to as the charge carriers are holes. And over here, in the N-type, we have our charge carriers being the electrons. But again, these devices are electrically neutral. We haven't split atoms, or we haven't done anything that way. You need to keep that in mind, but that's not the interesting part of this. But this piece is electrically neutral, as is the right side, or the N-type. What's more interesting is what's happening at the interface of this sandwich. If you have plain water and sugar water and you put them together, what's going to happen? The sugar is going to diffuse into the pure water, correct? Now we have P material and N material. The P is going to want to go to the N, and the N is going to want to go to the P. It's going to want to diffuse across that interface. Meaning now that we have this high concentration of electrons on the right, some of those are going to naturally want to migrate over across that interface. Likewise with the P-type. But if the P-type starts losing electrons, or if the P-type now has holes that have migrated to the right, what's left on the left-hand side? Electrons, which is, let's say, indicated by that negative column. In the N-type material, if our electrons have diffused over to the left, now we're left with protons or holes on the right. This now has basically established what's called a depletion. Region. We've now depleted electrons on the right, we've depleted holes on the left, and we now have established this electric field. Because we have this abundance of holes on the right, we have this electric field going from positive to negative across that interface. And that particular interface is given the phrase, or called a p-n junction. So we've now created this p-n junction by sandwiching together a p-type material and an n-type material. Or near this interface, or near the p-n junction, I'm now going to try to write down what I was just trying to say. The high concentration of electrons in the n-type material cause some of those electrons to diffuse into the p-type material. And just like the electrons in the n-type are wanting to diffuse across into the p-type material, the holes in the p-type material are wanting to diffuse into the n-type material. And I'll just say likewise for the holes. But that really doesn't go on forever, because once they start leaving, once the electrons leave the n-type material, they leave behind holes, some positive charge, and so the positive charge that are coming across, they're going, wait a minute, there's a lot of you already over here. So they don't keep diffusing across. There's a limit to that diffusion process, or this diffusion process is stopped by what you could think of as the bound charge, whether that's holes or electrons, the bound charge left behind. Where now let's just talk about what is left behind. For the electrons, those diffusing electrons leave behind inside the n-type material. So now if those were on the right, the electrons are trying to go to the left. Once they've left the n-type material near this p-n junction, those diffusing electrons leave behind protons, which you can think of as holes. Those diffusing electrons leave behind in the n-type material an uncovered, or a positive charge that's not paired up with an electron. So it's an uncovered positive charge. And that's bound in the nucleus. Of the atom where the electron left from, or the donor atom. And that same process is true for the holes that are wanting to go from the p-type material across the p-n junction to the right. And we schematically drew that picture. There's the bound positive charge in the n-type material. Here is the electron charge that's bound in those elements on the left in the p-type material. And anytime we have charge separation, we have a field. We now have this electric field that conventionally is from positive to negative. That's now our E field, or our electric field. And that electric field then is going to want to oppose movement across it, or this bound charge induces an electric field, and we called this particular region the depletion region. And this electric field puts up a slight barrier or establishes an energy barrier. That impedes charge flow. And that's why we really only have current going in one direction in this diode. Question?
Could you just clarify what you mean by an uncovered positive charge?
So what do I mean by an uncovered positive charge? That was up here. And what I'm meaning by an uncovered positive charge, which is going to be hard to maybe visually see if I'm using my hands to describe it, but we have in our atoms a proton and an electron paired up. Now in this N-type material, for example, which I think was on your right side, let's say this is the electron in my right hand and this is my proton. Now the electrons are wanting to diffuse over across that barrier. This proton is now uncovered. It's not mated up or paired with an electron anymore. So that's what I'm meaning by the uncovered positive charge. That uncovered positive charge is now what I'm representing right here on the right side in the N-type material. Likewise, if I did my thinking process on the P-type material, I have protons and electrons there. If the holes or the protons are wanting to move to the right, now I'm left with an uncovered electron, and that gives me the negative side. That separation of charge now with the positive and the negative gives me in the depletion region. The depletion region is where all of this has happened. Now I have an electric field established between the plus and minus. Question?
On the bigger picture of the entire diode,
Uh-huh.
we have most of the positive charge on the P type and the negative on the other side, and then at the depletion region it switches, and you have the electric field going this way. Wouldn't naturally it would want to go from large positive, the current would want to go from the large positive charge to the negative?
Okay, so now the question is, in my original picture, which way is the charge going to want to flow? Well, what we have to remember is in this picture, as I've drawn it so far, right here, I have not connected my anode or cathode to anything. So there's nothing there, and really this is just an electrically neutral material. Even though one is doped positively and one is doped negatively, it's an electrically neutral material. And I haven't applied anything yet to my anode and cathode, and naturally when I sandwich these together, because of the concentration differences on the N and P, the electrons wanted to go left and the protons wanted, or the holes wanted to go right, and that establishes this depletion region. And inside that depletion region, I now have this electric field established because of uncovered holes or positive charge and uncovered electrons on the right and left, respectively.
So is that electric field later on?
And now this electric field is what later on establishes this barrier that prevents or tries to stop electron flow or charge flow across that barrier. Are we done with all the words? I've been writing. Now you want to do pictures or circuits or something. Come on, get out of this. Well, you're all doped up, so it's not going to matter, right? Ha. No, I don't know. That wasn't very funny, was it? But these materials are doped up, and that's going to be to our advantage, is the idea. Here's what we have then. Remember what behavior we have? Here is our voltage across that diode. Here is our current. And we said that in the forward direction, if we apply a voltage across this diode in the forward direction, which means that we positively bias this diode it's going to naturally want to start conducting once we get a forward potential or a forward voltage across that diode of about 0.6 volts. And this is the region that we say we now have that particular element forward biased, or we're in the forward biased region. If somebody starts applying a voltage just the opposite direction of what I've indicated, or trying to look at a negative V sub D, and again, this right here, this might represent 1 milliamp. And if you want a better picture, look in the textbook. This is figure 10.2, hopefully. Now, if we start biasing this or turning the voltage around across that diode, now if I rescale the axis, so the positive side of my current is milliamps in scale, the negative side is now in the nanoamp region, I have very little current flowing when this particular device is reverse biased to a point. Once I reach, and now this is not drawn to scale, once I get sufficiently negative across that diode, it's going to give up and it's going to start conducting. Well, where does it give up? Quite a ways. I've now really hit this hard, but once I hit it so hard, it's kind of like we are. We finally just give up, right? So now if you reverse bias this by 100 volts, for example, then it will really start conducting current in the opposite way that we really would like for that diode to operate. This particular picture then is consistent with this schematic where our current that we've defined positive up above is going in the direction of the triangle, and the voltage is positive from left to right. This particular region, we've talked about the forward bias region, we've talked about the reversed bias region, and if we get too far in the reverse direction, we actually have a breakdown. And so this is now the reverse breakdown region.
It's to the left of negative 100 volts.
And that's, it depends on the diode, but in this particular example, I'm saying that process is going to, let's say, happen at minus 100 volts. And that's my reverse breakdown region. I ran out of room on the left, although I'm sure I could infinitely scroll to the left, but you would be mad at me because your page is 8.5 by 11. And you would go, how in the world am I going to go into my spiral bound margin if he keeps going left? Sorry. So we have now 3 different regions or modes of operation.
Is the forward bias region, is that past 0.6 in this diagram, or the whole right side?
It's the whole right side. The question was, is the forward bias to the right of 0.6? Forward biased is right of 0, but it may not really start conducting very much until you reach 0.6 volts. So it's really not turning on or opening that valve, so to speak, until you get beyond 0.6. Once you get beyond that, it's going to really allow the current to flow very easily, and you can then have a 0.6 voltage dropped across this diode and have as much current theoretically flowing through it as possible. So we have the 3 different modes of operation for this diode. Again, that's depicted maybe better than what I've sketched in figure 10.2. Now, if you just wanted to think about this in very general terms, you could say, well, let's just take that to the extreme or the ideal behavior. Which is in section 4 of chapter 10. And what do you think the ideal behavior diagram would look like? This is, let's say, more realistic as far as behavior. I have 1 nanoamp flowing when it's reverse bias. What do you think I approximate that by in an ideal case? 0. I have a forward voltage of 0.6 volts when it's turned on. What do you think I approximate that as? 0. So I just say, you know what, that's pretty small. If my circuit elements and values are such, let me just approximate that as 0 volts. Meaning if I positively bias this, I'm going to say, oh, I'm on. If I'm negatively, I'm off. Meaning I can support any current you want if I'm forward biased. So that's right here. That's the diode is on. And if I'm reverse biased, I'm right here and the diode is off. And to analyze diode circuits, a lot of times this might be an effective way to go. Just say, oh, if the diode voltage as we have labeled it or defined it is positive, then I'm just going to treat the diode like a wire. It'll have any current flowing through it and there's no voltage drop across it. In reality, there's 0.6 volts maybe, but we're going to neglect that and just say, oh, it's 0. We have a wire. If it's reverse biased and the polarity on that diode is negative, then we're going to say it's open. There's no current flowing whatsoever. It's like an open circuit. Let's look at analyzing a circuit under those ideal conditions. This is example 5 in chapter 10, hopefully. Suppose that I now have a circuit that is created in the following way. Let's say this is R2, and let's say that's 6K ohms, and let's say R1 is 4K ohms. And those are now diodes, ideal. Diode 1, D sub 1, and diode 2, D sub 2. In an ideal setting, if somebody said, oh, what's going to happen? Where's the current? How much current do you have? What's happening in this particular diagram? Can you tell me what's going to happen in that particular configuration based on what we've already talked about today? Can you tell me, is there going to be any current? What current? Is there not any current flowing? What's happening? And what are those diodes? Those diodes are one-way valves, aren't they? And in this case, it looks like, wait a minute, we've got valves going opposite to each other. And what you may want to do is, one way to analyze these circuits is to just say, you know what, I'm not sure what's going to happen, let me just make an assumption. And then I'll validate that assumption after I've made it. In this case, you have two diodes. What are my possibilities? They could both be conducting. One could be conducting, one could be off, and vice versa. Or they both could be off, right? So I have 4 different possibilities. Let's just hope that we get lucky and pick the right one to begin with. And you can sort of anticipate what's going to happen. Which way is an inductor, which way is a diode going to want to flow, or under what conditions? When it's forward biased, right? When the polarity across that diode is positive, from the anode to the cathode is when it wants to look like a wire. In this particular case, if you just looked at the sources and diode 1 is the anode, does it sort of look like it would be more positive than the cathode in diode 1? Because I have 10 on the left and 3 on the right. I'm maybe going to, if indeed there's current flowing out of the positive terminal on that battery, 10-volt battery, then there may be some voltage dropped across R sub 1, but I'm probably going to still have a voltage that's bigger than 3 volts that's on the cathode side of diode 1. Does that make sense? Your gut feel maybe is to say, oh, maybe diode 1 is conducting. Or we'll say diode 1 is on. So let's just try diode 1 on. Well, if diode 1 is on, and it's maybe at a potential of, let's just say it's something less than 10, let's say 8 for argument purposes. Let's say it's 8 volts on the right-hand side or the cathode side of D1. What did I say? It's 8. So what's D2? It looks like it would be negatively biased or reversed biased if I have on the left a higher potential than on the right. I really want, for that diode to be forward biased, I would want a higher potential on the right than on the left. So let me try D1 on and D sub 2 off. This is one of 4 possibilities. Or I'm now wanting to, well, if I now do that in my circuit, I can now re-sketch that. If that's what's happening, and these diodes are treated as ideal, diode 1 is now simply a wire. Diode 2 is what? It's an open, isn't it? It's not allowing current to flow. So that's like an open circuit. And there's my 3 volts here. This is 6K. This is whatever I said it was, 4K. This is 10 volts plus to minus. That's 3 plus to minus. I have a current then that would be flowing here, I1. And I have my voltage across diode 2 from the anode to the cathode, positive to negative, right to left in this particular diagram being V sub 2. I want to check whether or not this particular configuration is indeed what's happening. Or I'm now asking another question. I could say, is I1 actually flowing? Is it positive? And when I do the analysis, am I going to find that that V sub 2 is negative or that diode is reverse biased? Is that indeed what's happening in this particular picture? And what are we going to be able to do to analyze this? What we've been doing all semester, KVL and KCL. In this case, it's going to be KVL, right? You can write a KVL equation. How much current is flowing in the right mesh? 0. The only current flowing is I1, and that's in the left mesh, isn't it? So let's do that problem. If we now look at KVL, let's say around 1, I'm now going minus 10 plus R1 I1 plus R sub 2 I1. I1's not going to go towards the open. It's only going to go down. And now I'm back to where I started, and so there's 0. Or this tells me then that I now have R1 plus R2 times I1 equaling 10. And R1 plus R2, conveniently enough, this was 4 plus 6, wasn't it? K, 1,000. So I now have 4K plus 6K, or that gives me 10K, which allows me now to conclude that I1 indeed is positive, and it's 10 divided by 10K, or it's 1 over 1,000, or it's 1 times 10 to the minus 3, or 1 milliamp. And that's positive, isn't it? Which is greater than 0, so that checks with our assumption, with our assumed configuration. But we still have one more check to do. We need to make sure that V sub 2 is negative. What was V sub 2? If we go back to our diagram, how do we check V sub 2? KVL again, right? We do KVL, except now we need to make sure that we can do KVL across an air gap, and we can do that, right? V2 is just an air gap. Let's do KVL around the right mesh. And we can do that many different ways. How do we want to write it? Do we want to go clockwise from the center? All right, let's do KVL at 2. Again, what are we trying to do? We're trying to verify that V2 is negative. Let me go back to the figure. So now I have, if I go from the bottom middle node, which is the ground node, going from bottom to top up the 6K or R sub 2, what's my voltage drop in that direction? Negative, right? It's negative for what reason? I'm going against the current, and that current is, I'm assuming, positive down. So now that I'm going up, I now say minus R sub 2, I sub 1. Does everybody understand that? And then how did I label V2? It was negative on the left. So I'm entering the negative terminal of it first. I now have minus V sub 2 plus, is that right? I'm now going down the 3-volt source, plus 3 is equal to 0. I'm back where I started. So if I move V2 on the other side, I now have minus, what was R2? 6K. And what was I1? It was 1 milliamp, wasn't it? So it was 10 to the minus 3. Is that right? Plus 3 equals V sub 2. This K is really just 10 to the 3, isn't it? And so now I have minus 6 plus 3 equal minus 3. That's equal to V sub 2, and that's our second check. So we've now verified that our assumption was correct as far as how we wanted our circuit to behave. So now we know in that particular configuration that we created, D1 was conducting, it's on, and D2 was off. We've now verified or validated that assumption. Question?
I thought we wanted the voltage across it to be 0.
No, we want the voltage across that non-conducting diode or reverse bias diode to be negative. If it's going to be not conducting, we need that particular voltage to be negative across diode 2. Across diode 1, it's an ideal diode. We have 0 voltage drop, but it is in the current is flowing. Positive current is flowing through that diode based on the arrow of that triangle in diode 1. Oh, flooded with questions. On the left, in the P material. Sorry, I'm seeing the diagram. And our PN junction is right in the middle. Yes?
So doesn't it mean if we got negative voltage that it's actually flipped with what we want if you guys are showing that since we got a negative?
So now V2, as we've sketched it, is negative, which means what? It just means that the left node that is connected to our diode is more positive than the right node. And that's what would indicate that we had a reverse biased diode. The question was, if V2 is negative, is the voltage across that gap opposite to what we've indicated? And yes, it is. It's now negative from in the way that we've defined it. So it's now positive on the left and negative on the right. If it's positive on the left, which way was our diode going in this particular gap? This guy, if I remember right, wasn't he supposed to be like this? Isn't that how it was drawn? So now we've seen that this is 6 volts. So the cathode side is more positive than the anode side, which means it's reversed biased. It's not going to conduct. It's going to act like an open. Does that help answer your question? I wish I could say that last part. You'll just have to push rewind when you watch the tape. So the cathode, which is the negative side, is now more positive than the anode, which is the right side. I don't think that's what I said, but I tried to paraphrase because I forgot. It's getting late. Question? Yes, Cameron. And I know all 143 names. Yeah, right.
So, like, if you just, like, hypothetically, you just, like, pick the wrong direction or whatever, do you have to overhaul the math to do it over? Or
Okay, so the question was, what if I would have predicted or guessed that V2 was conducting and V1 was off? Oh, I'm sorry, D. Suppose that diode 2 I assumed was conducting and diode 1 was off. You would do the analysis and what would you find? Well, you would find that those particular assumptions were not correct. And so you would now say, okay, let me pick a different circuit configuration, which means let me now put a wire in where D1 was and open up where D2 was. You'll just have to go back and redo the analysis. Other questions? Before we finish, I know you're going to want to probably decorate the Christmas tree over Thanksgiving, or you'll put up some kind of lights maybe over the holidays. Let's talk about, and what do you now have that you're stringing up maybe? LEDs. Those are diodes. They're just light emitting diodes. But they work like a diode, which means that you might want to put up a power supply, a resistor, and then a diode, where that diode could actually be an LED. Meaning, if you get current to flow through that diode, it's going to illuminate. It's going to be bright, depending on how much current you push through it. If you push too much current through it, pew, it's going to be gone. It would have been bright for an instant, but now it's no longer going to work. And why do you think we have this guy there? It's a resistor. It's trying to impede current flow. So you pick that resistor to try to optimally determine how much current is flowing through that particular circuit. Let's say this is you go to a hardware store and you get a 10-volt battery. Not very common. Maybe I should have picked 9, but I can divide and multiply with 10 easier than 9. So just humor me. I now have a 10-volt battery. I now have a 2K resistor, which is pretty easy to find. So on Black Friday, you might, at 3 a.m., go to Radio Shack and get one of these. Go in and say, oh, I need a 2K resistor. It's 3 a.m. I know. I'm excited. It's Black Friday. I want to build a diode circuit. A what? Are you okay? I've been studying about doped silicon. Are you sure it's the silicon that's doped? I think. Sorry. So there's our LED. You put current through it. If I is positive, it's going to illuminate. What's going to happen in this circuit? Will that happen? Is the diode conducting? That's what you want to ask. And what's the circuit? You may feel very uncomfortable with this diagram. Somebody just labeled that node as 10 volts. Well, what they're really saying is the following. They've now put this is implied. That they have a source. And now we have current flowing in this mesh. Right? That's the implied concept. Now can you do the analysis? Now we could do a KVL. You're still at Radio Shack trying to figure out how to buy that resistor at 3 a.m., aren't you? But if we do a KVL, if somebody comes in Tuesday and shows me a resistor and a LED, that would make my day, huh? Especially if your receipt said 4:30 a.m. November 20 whatever, 6th. Okay, KVL. This is now minus 10 plus I times 2K. If this was an ideal diode, what would we do next? That would just be, let's just say plus VD equals 0, right? If it's positively biased, we need it to go from plus to minus, from the anode to the cathode. In an ideal world, or maybe we're just going to neglect that. We're going to say it's forward biased. Let's just assume that's 0. What do we know I is? I is now 10 divided by 2K. It's now 5 over 1,000, or 5 milliamps. You take it home and you go, oh, I can barely see it. It's barely light. It's barely lit. It's not burning very brightly. You go, it should have been 10 milliamps to make it brighter. Oh, what do?
Get a smaller resistor.
You get a smaller resistor. You go back to Radio Shack at 5 in the morning, and you purchase a smaller resistor. And you go home and you show your mom or your dad and you go, look at this. And it's entertainment. That's enough for now. We'll see you after the break. Have a safe break. And I do have your exams graded, and we'll return those if you want to come